Okay, so in this video, we're going to kind of see what's going on geometrically in this satellite radio example using GeoGebra. Okay, so we just, on Desmos, let me just remind us what we just did. On Desmos, we graphed this feasible set, okay, and then we found that the maximum occurs at 60/60. Okay, so now what I want to do is to use GeoGebra, which is kind of like Desmos, but to visualize what's going on. Now, in order to visualize what's going on, I want to just remind us what we talked about in the notes. In the notes, we talked about, where's the hover cam? Oops. In the notes, we talked about that linear programming is about optimizing these linear functions, okay, subject to some constraints, okay? So we want to maximize or minimize functions, okay, but we have to have some constraints in order for things to make sense, okay? So for example, in this simple example, y equals 2x plus 5, here, for example, x could be the number of days starting a new job, y is the money made from the job. If we just say maximize this, it doesn't make sense because you can take x to be any amount. It can be as big as you want it to. Okay, so like if you want, if you say choose any big number, okay, like 100, and if you put that into there, you get like 205. I could just say, okay, take x to be 101 or 102. This will keep going, okay? And that's because the function is a line. The graph is a line here, okay? It will go on forever, okay? It will be infinite, okay? But if I say maximize subject to this constraint, x is less than 7, greater than or equal to 0, now you got endpoints, okay? And the maximum is just going to happen at the endpoints, okay? That's what's happening here. Okay, and that's exactly kind of what the fundamental theorem of linear programming says. It says that, well, what's the fundamental theorem of linear programming say? It says that okay, so take a second. The maximums or the minimum values of the objective function is achieved at one of the vertices of the feasible set. Okay, so the feasible set, remember, is the solution set to your constraints. Okay, so if we go back to this one-dimensional case, which is very simple, this is actually the feasible set in this one-dimensional case, 0 to 7 here. Okay, and what the fundamental theorem says is that the maximum or the minimums will occur at the vertices, the endpoints in this case here. That's also similar to what's happening in the case of the satellite radios. Now the difference is that the satellite radios, we are optimizing a two-variable function here, okay? We got profit is equal to 12x plus 10y, where x is the number of model A radios, y is the number of model B radios. Oh, is this, oops, okay, let me get this out of the way. What's going on, okay, geometrically, well, some things to think about here is that we're now in the two-dimensional case. So in the one-dimensional case, we have one variable x, that's the input, and then one variable output, okay? Now, in the two-dimensional case, you have two inputs, x and y, and then one output, z, okay? Now, in the profit case, I can just call it p because p for profit, okay? And the idea is that any points in the plane, that's your inputs, that's your domain. And then the output is the z. So in order to graph these, you have to have 3 dimensions, okay? Now Desmos won't do 3 dimensions, so what we have to use is GeoGebra. So I'm going to close out this for a second here. Okay, so this is what we did in class on, or showed in class and also in the other video. The feasible set, and we saw that this is the maximum profit here, okay? Now, but what's actually happening, we have to go to the third dimension. So the third dimension is brought to you by GeoGebra. Now, GeoGebra is kind of like, it's kind of like Desmos. It's a similar type of platform, but it has a little bit more power to compute three-dimensional things, okay? So let me just pull out, where's the, 1 second here while I find the menu. No, that's not what I wanted here. Where's the menu of? Okay, so something weird happened. I'm not sure what's going on here, but it usually has these equations that show up somewhere. So let me actually refresh it. So let's just refresh it really quickly. Okay, so here are those equations here, and actually there's a small typo here, so I'm actually going to fix it here. Okay, so these right here are just the inequalities from the constraints. So I'm going to jump back here for a second. The constraints here, they're exactly these, okay? I left out the easy ones here, but these are the constraints from our satellite problem here, okay? Satellite radio problem, okay? So as you can see, so it's a little hard to see, so let me remove them first. But first of all, this is our 3D plane, okay? The red axis here is the x-axis. This is the y-axis, the green one. And then the z-axis is the blue, okay? So if I start plotting these inequalities, okay, well, what we see here is, well, okay, if I sort of position it so we're looking down at the z-axis here, and I maybe zoom in just a little bit here, okay, what we see is that feasible set, the thing that looks familiar to the feasible set. And let's just check our intuition here, okay? So it's a little hard to see because I have to move this in a little bit, but you can see that you have this this like quadrilateral here, okay? And this is that feasible set. Now, it doesn't look quite it because the rendering gets better when we zoom in, but hopefully you're convinced now that this is the feasible set that we looked at in the last video, okay? So that's what this is here, okay? So now, what are we going to do? Okay, well, what's going on geometrically? We have this profit function. So I'm going to open up GeoGebra big now, if we're okay now that that's what's going on there. Oh, I think you click on this calculator and this comes out here. Okay, there we go. Okay, and what I'm going to do is I'm actually going to type the profit function. So what's the profit function? It's it's this 12x plus 10y. That's the profit. Okay, so I'm going to type that in, and maybe I'll say p equals 12x plus 10y. Okay, and as you can see, what we get here is kind of this piece of paper here. It looks like a plane here, okay? This teal thing is the analog of a line in 2 dimensions, okay? So the graph of a linear equation, if I open up another Desmos here, okay, so Desmos. Okay, if we just do 2x plus 5 like I did in the simple example, the graph of a one-dimensional equation here is a line here, okay? So that's what this is, okay? Now if we have 2 variables, the graph of a two-dimensional, 2-variable equation is a plane. It's like a piece of paper, infinite piece of paper. Now as you can see here, it's a little hard to see, and I'm not sure how to get the settings to work out here, so I think we would have to zoom out, but that might mess up the rendering. But basically the point is that if we zoom out kind of far here, okay, and how far are we going to zoom out, Jackson? Maybe just a little bit, okay, just a little further here, okay. You can see that, well, maybe you can't see, but you can see perhaps that the maximum is going to occur at the vertice that's the highest on this graph here, okay? So it's a little hard to see. Let me maybe try to plot a point here. And that, what we figured out was 60, 60 was the maximum, where we're going to have maximum, the maximum profit was 1320. That's what we figured out, okay? Okay, so that is kind of hard to see on here, but I'll link this so you can play around if you want to. But this is where the maximum exists, above the 60-60 here, okay? And that's what's going on here. We're just finding the maximum. It's kind of similar to finding the maximum on the simple example. It's just we have to do more work. We have to do some algebra here to figure out this point here, okay? And maybe something that's a little bit easier to see is that the minimum is at 0, 0, okay? That's the minimum. And it's just, you can tell because of the way the paper, or this plane is tilted, okay? Anyway, just wanted to show this here. This is a good way to see what's going on, even though it's not as good as Desmos in terms of the graphing here. Okay, thank you.